Local AI has been getting better fast, but it still usually feels like a compromise. You can run smaller models, and you can make a chat app respond locally. But that's not the same as putting local AI to work. That is starting to change. Open models are getting better, they're getting more useful, and maybe most importantly, they're getting bigger. I have two ASUS GX10s here, and together they give me a 256 gigabyte local AI cluster on my desk. One GX10 is the practical test. Can I run a useful local coding model and actually get work done? And two GX10s are the bigger model test. Can linking two of these together move me into a class of models that normally feels out of reach for local hardware? I want to know what these are actually like to use. So I'm going to put it to work with an agentic coding workflow, something closer to how people use tools like Claude Code. The model has to plan, edit files, run commands, fix errors, and build a real homelab app. Because the real question is not whether local AI can run, it's whether local AI is getting big enough and useful enough to actually matter. And this is where local AI gets interesting, because it's not just about the model. I'm not just testing whether a local model can run, I'm testing whether the whole local AI system can be something that I would actually use. So with that in mind, this is the hardware I'm using for the test. These are the ASUS Ascent GX10s. It's a lot smaller than it looks. It's a lot heavier than it looks too. One of them by itself is already interesting because the idea is that you can get a small local AI box that can sit on your desk instead of building a giant workstation or adding another server to the rack. And this is not just a normal small computer. Inside of each one is NVIDIA's GB10 Grace Blackwell platform. So you have an ARM CPU, a Blackwell GPU, and 128 gigs of unified memory in this really small box. Local AI is usually not about, can I run this? And it's more about how big is the model and can I fit it into memory? It's crazy to think that there's 256 gigs of RAM right here and two Blackwells just right here in my hand. That's a lot of power. That's a lot of memory. Now that doesn't mean that magically every workload treats this like one giant pool of memory. The software still has to know how to use both machines. The other important piece is networking. Each GX10 has a standard 10 gigabit Ethernet port, but the important part for this test is the NVIDIA Connect X7. All right, and here is that QSFP 112 cable. Plug it into here, into the second one here. That's a tight. That's what lets me link two of these machines together and try to treat them as a cluster instead of just two separate computers sitting next to each other. I learned that these have magnets built into them, which I think is pretty cool. If we put this first one down, stack this on top, you can kind of see that. So there's a magnet. I'm not just looking at whether it runs. I want to see how these machines behave when they're actually working. I have each of these on their own smart switch so we can see how much power they're pulling. I'm really curious when they're clustered, if they pull the same amount of power or if one's doing the workload and doing most of the work while the other's just hosting memory, and how much power that pulls together. And I'm watching temps, utilization, and system health in Grafana, because if this is going to work as a local AI system, I want to know what the machines are actually doing under load. The next question is how I actually use it, because I'm not planning on sitting in front of it with a monitor, keyboard, and mouse every time I want to run local AI. I want them to feel more like a remote AI development machine. I don't want to move my whole workspace over to the GX10. I want my normal computer to stay my main machine, and I want the GX10 to become the machine doing the AI work in the background. I'm comfortable setting up SSH keys, remote access, VS Code remote, port forwarding, and doing all of that myself. But NVIDIA Sync made this a lot easier than doing everything manual. And the VS Code part is pretty cool. It installs the remote VS Code server on the GX10, tunnels back to my local VS Code, so I'm still working on the editor on my main computer, but the workspace is actually on the remote machine. And when I open the terminal inside of VS Code, that terminal is not running on my main computer, it's actually a shell into the GX10. The next problem is storage. And then we have a 10 gigabit Ethernet port, and this is actually really handy because I'm going to store my models on my NAS and connect and pull them down that way. When you're downloading models that are 40, 50, 60 gigs and some upwards of 200 gigs, that space runs out really quickly. Now that the models live on the NAS, I need a way to actually run them. There are a bunch of ways to run local models. Ollama is probably the easiest place to start. Llama CPP is a lightweight option that works well on a lot of hardware, and Docker Model Runner is interesting if you want models to fit into your Docker workflow. But for this test, I'm using vLLM. On that first node, here's how I'm spinning up vLLM. I actually have an Ansible playbook that does this, but this is the compose file that it creates. What you can see is I'm mounting this to my NFS share. vLLM is more of a model serving layer. It's built for running models as a backend that other tools can talk to, instead of just being a simple local chat experience. So once you start up that container, you can see vLLM is starting. You can see a lot of things starting to happen. Now, after it's running, I'm seeing these metrics, health checks. I wired up Grafana and Prometheus, of course, to these so I can get some really rich metrics. So the basic flow is pretty simple. The model files live on the NAS. The GX10 loads the model over the network into memory, and vLLM serves it as a local model endpoint. Now that I have a local model server, I need something that can actually use it. And this is where OpenCode comes in. Open up VS Code, and you can see that I'm SSH'd into that first node by using that NVIDIA sync. And what I want to do is I want to open, I actually want to open OpenCode from here. If I wanted to get really fancy, I could open something like btop here. Then I can open yet another terminal, and I could do something like docker logs vLLM follow. So now I have this little console where I can see the files getting created. I can see what's going on with the server itself. I could see some logs in case there's some errors, and then I could see what the agent itself is doing. For this test, I picked OpenCode because it's open source. It works well from the terminal, and it can work with different models. OpenCode can also run as a web app, which means I can serve it from the GX10 and get back to my sessions from a browser as long as I can reach that machine. So the stack for this test is pretty simple. The GX10 runs the model, vLLM serves the model, and OpenCode gives the model access to the project and terminal. Now we need something for the agent to actually build. So I landed on a homelab service tracker. It's a small web app for keeping track of services in a home lab, things like Proxmox, TrueNAS, Grafana, Plex, and Pi-hole. I give it a pretty detailed prompt with the stack, the scope, the data model, the test requirements, and the definition of done. I also told it what not to build, and that was intentional. I wanted a task that was real enough to exercise the agent, but not open-ended so it could wander off and build something else or be impossible to judge. I also asked it to create a spec, task, agents, and a progress file before implementation, and then work through the project step by step. Sometimes agents will go through and build the whole entire application and then go back and test it, and things can be a mess. I'm guilty of doing that. So I'm trying to give it some guidance like I would another developer. Say, hey, let's develop a feature at a time, run your checks, write your tests, do your linting. Once that feature's done, kind of move on to the next one. The idea was to force it into more of a structured coding agent workflow and keep going until the project is actually done. So this is not a perfect scientific benchmark, it's a practical test. Can this local AI workflow build something useful? And for the first real test, I'm starting with one GX10. For this run, I used Qwen 3.6 35B A38 FP8. Here we can now give it this prompt, and it says, hey, we pasted around 229 lines into here. Hit enter, and let's see. We'll watch his thinking a little bit. So you can see it created the to-do list. This is one thing where, that's interesting. This is the human in the loop, so it's asking for permissions to do something. Everything from /over, I think that's a lot. I would think it might need access to temp. This is on that machine it's contained. It's not on my own machine, like my Mac that I'm working on right now. I am gonna give it access to this only so we can move this demo along. But you can see, hey, it's creating the agents. It's creating the progress file, which it already said it's done planning and it's moving on to the end progress. Now it says it's thinking, but it's not really thinking right now. If we go back to our vLLM dashboard, we can see it's really not doing anything. So this is kind of what I was hoping it wouldn't do, is get stuck. So I just told it continue. That's gonna be my default. If something goes wrong, I'm gonna say continue. I don't wanna try to give it any hints or any prompts or influence what it's doing other than just proceed. It looks like another tool call. This is kind of where sometimes local models kind of break down. I'm gonna keep giving it the continue prompt and we'll see what it does. Okay, it is claiming that it's done. And let me do a Docker compose up build and have it build it again. Okay, so now it's on 3100. And if we go out to 3100, hey, here it is. So we can see it's actually running. We can see we have categories, virtualization. Is this actually sorting? I don't think it is. That doesn't seem to be working. I kind of jumped the gun. Let's see if our CRUD works. Let me update something like Grafana's and let me set it to offline. Can we save this change? Interesting. So I'm getting a 405 on here. Something is definitely not working. Let's actually give it a little bit more context. When I run the application, edit, filter, and save do not work. Please fix this and write a regression E-to-E test when you fix it. Yeah, it's really in a loop, so I'm going to interrupt it. I'm going to say, please focus on making filtering working first. Use the web to look this up. There we go. So I think it just needed a little bit of a nudge to say, hey, go use the docs and don't use your own memory. It just went out to the documentation, figured out how search params really worked, and then it seems like it fixed the bug. Here it is again. Let's see if it works this time. Let's do a filter now. Hey, it's working, Grafana. So that was the single node run, and the good news is that it did build a working app, but it definitely wasn't hands-off. It got stuck in tool calls, it asked for directions, it struggled with tests, it broke the remote workflow by killing the wrong node process, and Docker, database configuration, and testing took a lot of steering. To be fair, I don't think every problem here was necessarily the model. Some of it could be the model, some of it could be OpenCode, and some could just be the way that all of these pieces interact. It built the app, it got some things wrong, I had to steer it more than I wanted, but overall, the workflow worked. So my takeaway from the OneGX10 test is, yes, it can do some local coding work, but I would not call it autonomous just yet. Here it is in Home Assistant. This is my first plug and my second plug. So blue is node 1, orange is node 2. Of course, node 2 isn't doing anything. We can see that this is using some power, anywhere from about here, which is 127 watts, 125 watts, so anywhere from 0 to 125 watts. At idle, with this model loaded right now, it's using 50 watts. So even though it has a model loaded and it's not actively doing anything right now, it's using 50 watts of electricity. So if I were to keep this on 24/7 and it wasn't doing anything at all, just keeping that model in memory, it's going to cost me about $4 or $5. The tooling is free, but electricity and energy is not. That leaves the second question. If OneGX10 can already do useful local coding work, what does adding another actually change? Does a larger model make the agent more capable? Or does it just add more power draw, more setup, more complexity, and more things that can go wrong? That is what the second GX10 has to prove. But before I can run a larger model across both machines, I need to make sure that the 2-node cluster actually works. This is where NCCL comes in. Now, NCCL is NVIDIA's library for getting GPUs to communicate efficiently across multiple devices or multiple machines. 2 machines are connected over QSFP Direct Link, and vLLM is set up as a 2-node Ray cluster, with one GX10 acting as the head node and the other as the worker. I ran the NCCL tests, and the good news is that the link worked, but the results were not quite what I expected. Let's just say 16 times 8 bits in a byte, so 128, so about 130 gigabits per second, so that's definitely slower. But I was expecting something closer to the 200 gigabits per second, so I went down the rabbit hole for a while. I also ran some lower level RDMA tests, and those showed really low latency, so the ConnectX link itself was clearly working. But NVIDIA says that GPU Direct RDMA is not supported on the GB10 systems, so this is not the same as GPU to NIC path I originally had in mind. I eventually had to stop chasing this perfect number. From there, the next step was configuring vLLM to actually use both machines for the larger model. Now that the 2 machines are linked and NCCL was working, I can finally try the bigger model test. The goal was to find a model that didn't really make sense on one GX10, but then might work when I linked 2 of them together. That was actually harder than I expected it to be. A lot of newer models were either small enough to fit on one machine, or so big that even 2 GX10s were not enough for the way that I wanted to run them. Then Minimax 2.7 had just come out, and it seemed like a really interesting fit. One thing I will mention is that even though we have 256 gigs of RAM to use across both nodes, this Minimax M.2 is cutting it really close. But once I had it, it kept starting to load and then crashing. And this is where I learned that the model file size is not the whole memory story. You also need room for the KV cache, which is memory the model uses in order to keep track of the context while it's generating. So what I ended up doing was I found that someone quantized this right here, this AWQ 4-bit, so it's a little bit smaller and probably a little less accurate, but still it's based on Minimax M2.7. And the big model is finally loading across both GX10s, but getting here was not as clean as I hoped. It's been about 2 days since I said let's work on Minimax M2.7. I got it working, but I was only getting around 26 to 28 tokens per second. I just thought that was okay. But when I checked Spark Arena, I saw that people were getting 40 to 38, which is almost double of what I was getting. That turned into a whole bunch of tweaking, compiling a whole bunch of stuff, swapping out versions of vLLM and different versions of different libraries that we were using. Finally figured out what it was, and it was as simple as running the vLLM container as privileged. Eventually, I got closer to 41 tokens per second, which felt more in line with what I expected from the 2-node cluster. But now that the model is up, and both GX10s are being used, I can finally run the same coding agent test against the bigger model. So I'm starting from the same idea: OpenCode, the local vLLM endpoint, and the homelab service tracker task. But this time, the model underneath the agent is running across both GX10s. All right, yeah, this is cool. So this is a little bit smarter already. So what it did was make a folder called app temp. And then what it did was use create next app latest. So this is a little CLI tool to generate a Next.js application. This model was smart enough to actually run the generator to generate the application, and that will scaffold out the entire application. Whereas the first model, it did it all manually. It created the package.json and it injected a whole bunch of dependencies. So this was already smarter. All right, so it says it's up. It's running on localhost 3100. Does it filter? Hey, it does right away. Monitoring. Hey, it works. All categories. Grafana? Yeah, it's working. Our text isn't the greatest color though, but it's working. But let's change one of these. So Pi-hole, I'm going to change each one of these just to make sure that these attributes persist. So it did. Let's do a refresh test. Hey, it's working. Now let's try our delete. Whoa, well, we did get a dialog. Let's delete it. There it goes. Let me refresh. So it did persist. Now let's add our own service. I'm going to say it is code server. Okay, save. Code server, hey, there we are. Okay, if we see here, this is probably when the model was loading up, then it was waiting for input when I launched OpenCode, and here it is, just taking off and working. So it's pulling about 150 watts right now for both of them. Yeah, total 330 watts right now. So it's really drawing some power for both of those together. And you can see right here, the cost per month, if it ran, at this 284, 300-ish watts, all month, this would be costing me $20. So that was the 2GX10 run with Minimax 2.7. This was much closer to what I hoped the agent workflow would feel like. It was still not perfect, and I still had to pay attention. So it's trying to kill the dev server. Don't want to intervene, but it looks like it might be having some problems. But the overall run felt more capable than the 1GX10 test. The model followed the task more cleanly, made better choices, and the final app turned out to be pretty good. That doesn't automatically mean that the second GX10 is worth it for everyone, but this is the first point in the test where the second machine really felt like it changed the kind of local AI workflow I could run. So now I have both runs, one GX10 with Qwen 3.6, 35B, A3B, FP8, and two GX10s with Minimax M2.7, AWQ 4-bit running across both machines. This means it's not a pure model benchmark, it's more of a workflow comparison. But after the benchmark was done, I kept pushing the agent a little bit further, because once the app exists, the next question is whether the agent can keep improving it. Hey, look at that. It does look a little bit better. It actually looks a lot better. Nice fonts here. We have these nice badges, nice colors. This actually looks nice too. This is the daisy dropdown, and it has the checkbox for the one that's selected. You notice too that the text isn't all light and hard to see. Very clear font. Search Grafana, yep. Let's delete Grafana, yep. Oh, so this is the daisy dialog, much nicer. Delete, hey, look at that. An empty state, that's pretty nice there. It has some icons in there. It pulled in daisy UI, updated the interface, improved the forms and buttons, and made the app feel much more demoable. Then I gave it a ridiculous test. I asked it to redesign the whole UI like a Windows XP desktop. Let's do a refresh. Hey, oh man. Oh man, this is actually pretty awesome. We do have a clock down here that is the right time, which says all systems operational. It's pretty cool. Wi-Fi or network signal, we're connected to homelab network. Volume control, this can't be real. This can't be real. I don't think it is, but it is really cool. Look at this start menu. Let's see, start. Here's all of my services right here. So all services, can I click on that? Oh, open. Oh, look at this window. Oh, I can even move it too. Can I full screen this? Oh yes, this is awesome. Let's look at a couple more things right here. So let's see, Proxmox. Whoa, whoa. I can see what it did. So this is a screen with it in there. Proxmox is in there. That is not good. This one was mostly for fun, but it was actually a good stress test for whether the agent could make a broad visual change across the whole entire app and then respond to follow-up fixes. Before I get into my final thoughts, I think it's worth being clear about what this actually takes. Because this is not plug and play. The hardware is impressive, the models are impressive, and the fact that any of this runs locally is really impressive too. But getting all of the pieces working together still takes real effort. There was also one weird behavior that I ran into while compiling NCCL. The machine didn't fully lock up, but it stopped responding over SSH. My sessions disconnected, all the CPU cores were pegged at 100%, and once the compile finished, I could SSH back in again. I did reach out to ASUS about it, and they said they couldn't reproduce it on their end, but since I could reproduce it, I thought it was worth mentioning. And on top of all of that, the model landscape is moving ridiculously fast. The model that looks like the right choice one week might not be the right model choice the next week. But that's what you should know going in. You're not just running a model, you're running the model, the serving layer, the agent, the storage, the network, the monitoring, and the app you're trying to build. And when something breaks, it's not always obvious what layer caused it. And that's the part I want to be clear about, that this is a powerful stack, but you also kind of have to understand it. So where do I land on this? After spending a lot of time with the GX10, I think the simplest way to put it is this. One GX10 makes local AI feel practical, and two GX10s make larger models possible. But neither version makes local AI effortless. And that's probably the most important thing to understand. These are not cheap machines, and even though the ASUS GX10 is one of the most affordable versions of the GB10 platform, it's still $3,500, and that's a serious purchase. And if you buy two, obviously that doubles the cost, then you also need a cable to link them together, which is around another $100. So I would not look at this as a cheaper way to avoid an LLM subscription. That might be part of the story, but it's not the whole story. You have to set your expectations. For a model this size running locally across two desktop machines, that's pretty impressive. But it still doesn't feel instant in the way that some cloud coding agents can feel, so you have to be realistic about what fast means here. I can point an agent at a project, let it work in the background, and use it for the kind of work I normally avoid. That is where I can actually apply some of this. I have old projects that have tech debt. I have an Android and iOS app that was recently delisted because I haven't kept it updated with the latest libraries from Apple and Google. Classic tech debt. That kind of work is not glamorous. It's a slog. But it's exactly the kind of thing where I could see a local coding agent being useful. Not replacing me, not magically fixing everything, but chipping away at the work and making updates, trying fixes, running tests, and giving me something to review. And that's a version of local AI that feels real to me. So who is this for? I think it's for developers, researchers, and serious AI enthusiasts who actually want to build on the NVIDIA platform. If you want to learn the stack, run local models, test agent workflows, or build something locally that could eventually move to a bigger NVIDIA infrastructure, this makes a lot of sense. If you build it here, the idea is that you're working on the same general ecosystem that you would use later on bigger systems. But if you're not comfortable with spending time in a terminal, reading logs, changing settings, debugging Docker, tuning vLLM, or dealing with weird issues as they come up, this is probably not for you. For a lot of people, one GX10 is probably the sweet spot. It gives you 128 gigs of unified memory, a compact local AI machine, good cooling, and enough capability to run useful models and real coding agent workflows. 2GX10s are much more interesting if you specifically want to push into larger models. But with 2 also means double the hardware, more power, more tuning, more complexity, and more things to debug. The GX10 is not the easiest way to run local AI, it's not the cheapest way to run local AI, and it's not some magic replacement for cloud coding agents. But it is one of the most interesting local AI machines I've ever tested because it makes the whole workflow feel possible on a desk. 1GX10 made local agentic coding feel practical, 2GX10 made a much larger local model possible, and that's the real takeaway for me. Local AI is getting big enough that the hardware matters again. I'm Tim. Thanks for watching.